All right, in this section, we're going to finish up our convergence test. There's two more tests we can run to see if a series is convergent or divergent. These are the ratio test and the root test, and we're going to start with the ratio test. So we begin with a series that has non-zero terms, and we just evaluate the limit. We're not making a comparison. We don't have to come up with a new series to compare it to. We are comparing successive terms in the same sequence. So I'm forming the fraction an plus 1 over an, so it's the subsequent term that goes on top. And I'm taking that limit of the absolute value of that ratio as n approaches infinity. And if that ratio is less than 1, or if that limit, rather, is less than 1, then the series converges. If it is greater than 1, the series diverges, and if it is equal to 1, we're not sure. It's inconclusive. We have to find some other way to analyze the series. The ratio test is kind of a way to say, as n gets big, does our series start to behave like a geometric series with an r that's less than 1? Obviously, that r is not constant. You know, what makes something a geometric series is that that ratio is always one value. But we're just trying to say, as n gets big, does the ratio approach a value that's less than 1? So we're going to do some examples. We're going to determine whether this series converges or diverges. So we're going to use the ratio test, and the first thing I do when I am using the ratio test is I just write out my terms a sub n and a sub n plus 1. A sub n is the easy one. It's the one as it appears in the series as given. So 2 to the n over n factorial. And then a sub n plus 1, that's 2 to the n plus 1 over n plus 1 factorial. Now we're going to set up our limit as n approaches infinity. Absolute value of a sub n plus 1 over a sub n. Now notice that our terms, a sub n, they're all positive, right? I mean, 2 to the n over n factorial, for all infinitely many terms in this series, they're all positive. So for that reason, I'm not going to include the absolute value signs. We can dispel with those. So a sub n plus 1, I'm going to start there, 2 to the n plus 1 over n plus 1 factorial. And now we're dividing by a sub n, so I'm going to multiply by the reciprocal, n factorial over 2 to the n. Now we've got some algebra to do. First, we can cancel a bunch of 2's, right? 2 to the n cancels with all but one factor of 2 that's up top, so I'm retain one factor of 2. And now, to deal with these factorials here, I just want us to remember that n plus 1 factorial is equal to n factorial times n plus 1. Right? Like it has all the factors all the same factors that n factorial has, plus the additional factor of n plus 1. So I'm going to use that to rewrite the denominator. So now I've got 2, up top I have 2 times n factorial, on the bottom n plus 1 times n factorial. So now the n factorials cancel. This is the limit as n approaches infinity of 2 over n plus 1. And that limit is 0, right? I've got a constant numerator. The denominator is approaching infinity. That means this limit overall is 0. And the thing that we need to observe, we actually have to explicitly observe this because of, there's different convergence tests, and we're always evaluating different limits. So what we need to observe here is that 0 is less than 1. And that means that the test is conclusive, and our series 2 to the n over n factorial converges. Let's try another one. We're going to use the ratio test here again, so I'm going to start by writing out here our nth term is n squared times 2 to the n plus 1 all over 3 to the n, and a sub n plus 1, that is n plus 1 squared times 2 to the n plus 2 over 3 to the n plus 1. So now we need to set up the limit as n approaches infinity, absolute value a sub n plus 1 over a sub n. Again, you know, all of the terms of this series, they're all positive, so we don't need to retain the absolute value signs here. So I'm going to begin with, here's our a sub n plus 1. And then we're dividing by a sub n, so multiplying by the reciprocal. We could do some canceling. So let's see what we got. The 3 to the n will cancel, and we're left with 3 to the first on the bottom. 2 to the n plus 1 cancels down here. We're left with just 2 to the first on top. So we have 2 times n plus 1 squared over 3n squared. And I guess we have a couple of options as far as dealing with the algebra here. One thing that might be simple is if I'm looking at just sort of like this part, I'm going to rewrite that. They're both squared, right? I've got n plus 1 squared over n squared, and that's the same as n plus 1 over n all squared. So I'm going to rewrite it that way. I've got my factor of 2/3, n plus 1 over n squared. I can rewrite that fraction. I could split it up over the addition up top. So that's n over n is 1 plus 1 over n squared. And now as n approaches infinity, 1 over n approaches 0. That means that this approaches 1, or 1 squared, so which is 1. And overall, then we're multiplying that by 2/3. So overall, this limit is 2/3. And what do we need to observe about this limit? We need to observe that this is less than 1. And because it's less than 1, that means that this series converges. Okay, let's try another one. This series, the nth term is n to the n over n factorial. So a sub n, n to the n over n factorial, a sub n plus 1 is n plus 1 to the n plus 1 over n plus 1 factorial. And now we're going to set up our limit as n approaches infinity. Absolute value a sub n plus 1 over a sub n. Again, all these terms are positive here, so we don't need the absolute values. When we see, you know, like times when we just have to pay attention to the absolute values would be like if we have an alternating series maybe, or a series where the signs can change at all, and we just say let's just make all the terms, you know, positive. We'll ignore the sign changing part of that series. So, all right, what do we got here? We start with a sub n plus 1, so n plus 1 to the n plus 1 power over n plus 1 factorial times, and now I'm going to divide by a sub n, so multiply by the reciprocal, n factorial over n to the n. We're going to rewrite this, and mostly what I'm going to do right now is, oh, you know what, I just wrote the wrong thing here. And so this part here should be n factorial over n to the n. So maybe you already caught that, but... Okay, so now I'm going to start with, I'm going to rewrite this n plus 1 factorial. I know that's equal to n plus 1 times n factorial. I'm going to do that at the same time. This n plus 1 to the n plus 1 power, I'm going to write that as n plus 1 to the first times n plus 1 to the n. Anytime I have a series with a lot of, with any factorials, usually the ratio test, just jumps out at me as being a good thing to use, because there's a lot of canceling that happens when you're dealing with factorials. So here we could see the n factorial cancels with the n factorial there. And then we have this factor of n plus 1 canceling with this factor of n plus 1. So now I'm going to bring this over here. This is the limit as n approaches infinity of n plus 1 over n all to the n power. And I can split that up just like I did in the last one. And I get 1 plus 1 over n to the n power. Now, this one isn't really... this is where the similarities with the last one ends, because before, up here, I had 1 plus 1 over n squared, right? So that just, this power here was constant. But here, our exponent is increasing. So we need to evaluate this limit as n approaches infinity. This takes a little bit of doing, but lucky for us, we've already done it at least twice in this class before. We've done it in the section on L'Hopital, and I think we did it back in maybe even chapter 1. So maybe you recognize this limit, and if you don't, I'm just going to go ahead and give away the surprise here. Hopefully not a surprise. This limit is e. This is one of the ways to define the number e, is the limit, is this limit. And e, what do we have to observe about e? Is that it is greater than 1, right? It's about 2.718 and so on. If that's greater than 1, what does that mean about our series? That means that our series has to diverge. All right, so there's a few examples of using the ratio test. Again, I almost always use the ratio test, or it's one of the first things that comes to mind if I have a series with factorials in it, just because you get a lot of canceling to happen. Next, we're going to look at the root test. This is good for a series that involve an nth power. Basically, it just says, if I look at the limit, and again, I don't have to come up with a comparison series, right? I'm creating a limit and examining that limit based on just the nth term of our series. So we're looking at the limit as n approaches infinity of the nth root of the nth term. And then just to make sure, if there's any sign changing, we make sure we just make them all positive. So the absolute value of the nth term. If that limit is less than 1, it converges. If that limit is greater than 1, it will diverge. And just like with the ratio test, if it's equal to 1, it's inconclusive, and we need to try something else. So let's examine this series. The nth term is e to the 2n over n to the n. and, you know, where n starts at 1. All the terms are all positive, so I don't have to worry about any absolute values. But in this problem, you know, we want to examine the limit as n approaches infinity of the nth root of absolute a sub n. So that's the limit as n approaches infinity of the nth root of e to the 2n over n to the n. I'm going to rewrite this nth root as a 1 over n power. So I have the fraction e to the 2n over n to the n, all raised to the 1 over n power. Now we can distribute an exponent over division. So I'll just apply that exponent to both the top and the bottom, and when we raise a power to a power, we are multiplying them, so that becomes, let's see, I'm going to come back here, limit as n approaches infinity of e to the 2n over n to the n over n. So I have e squared over n. So now this limit as n approaches infinity, I think now we're ready to evaluate. E squared is a constant, and I'm dividing that by n, and as n approaches infinity, the bottom is blowing up, the top is staying put, so that means overall this limit is 0, and the thing we need to observe about this limit is that it's less than 1, and that means that the series converges. All right, let's try another one. We are going to evaluate the limit as n approaches infinity of the nth root of the absolute nth term. It's a limit as n approaches infinity of the nth root of n cubed over 3 to the n So I've got basically the nth root of n cubed over the nth root of 3 to the n, and doing the algebra, we get n raised to the 3 over n over 3 raised to the n over n. So we have the limit as n approaches infinity of n to the 3 over n divided by 3. So as n approaches infinity, obviously the denominator stays put at 3. The question is what happens up top. And as n approaches infinity, this is approaching, let's see, the base is infinite, is growing. The exponent is approaching 0. That's an indeterminate form. So we're going to use L'Hopital. And in fact, we're going to, it's not a form we can use L'Hopital on directly right now, but I'm going to do a little side work. We did L'Hopital toward the end of the last chapter, so hopefully this is roughly fresh. But I'm going to let y equal this limit, and I'm really just going to focus on the top. So n to the 3 over n. And then whatever I find here is what we could put in that numerator. So now I'm going to take the ln of both sides. So ln of y is equal to the limit as n approaches infinity of ln of n to the 3 over n. Of course we do that so we could take that 3 over n power and bring it down as a factor in front. So I'm going to rewrite this as 3 ln n over n. Now, as n gets huge, 3 ln n approaches infinity, n approaches infinity, so this is type infinity over infinity. That means we can use L'Hopital. And when we use L'Hopital, and I'm going to just go ahead and leave the n's in here for now, but this is would be 3 times 1 over n divided by 1. That's ln y. And as n gets huge, 3 over n becomes close to 0. So we found that ln y is equal to 0. What we wanted was y. That means y is equal to e to the 0, which is 1. And so the limit as n approaches infinity of n to the 3 over n is 1. And that's what I'm going to plug in up here. So the top, the stuff in the dotted box around up top, that's approaching 1. And the thing we want to observe about this result is that this is less than 1. And so that means the series converges. All right, so that's our last example. What I want to do, at the end here, that's our last example in this section, but it's this section is sort of the last of our different convergence tests that we have. Okay, so if you just encounter an infinite series, say out in the wild, or as you're doing exercises, and you're trying to figure out what that infinite series does. Here's sort of a list that I kind of run through as I'm thinking about a series. Almost always the first thing I do is I just say, does the nth term approach 0? If that's like an easy limit to kind of just assess, I'll see if it approaches 0. If it doesn't, then I'm done, right? The series diverges and I'm done. If it does approach 0, that means I have more work to do. I see if it's a special kind of series, if it's geometric or p-series, those we pretty much automatically know with very little work what it does. The alternating series, we can use the alternating series test if it's a telescoping series. So if it's a special kind of series, then I just try to recognize that and use the tools that we have. After that, I just see maybe I could apply the integral test or the ratio test or the root test. Usually the last thing I use is a comparison test unless something really jumps out at me. Because with a comparison test, we have to come up with a whole comparison series and see what that does. Now, I'm not trying to say that this is the absolute order in which you should think of things. I am saying that it's one thing, if I'm not unless something really jumps out at me when I first start looking at a series, this is roughly the kind of sequence in which I try things. And then just this last page is just a summary of all of our convergence tests. I would have this page bookmarked, as you're working on a test or an assignment, just to have it handy. That way, especially on a test or something that's timed, you don't have to flip through all the pages looking for your tests, like your convergence tests. They're all here and summarized for us to use. And that'll do it for this section.